Okay, so this morning I would like to go on with the exercise that we started yesterday. So the problem yesterday was to investigate a simple cubic lattice. We used at the beginning yesterday we found the general expression for the energy versus V vector dependence. So this was the general expression considering the application of the type binding approach to the case where we have again a simple cubic lattice where the distance between the ions in the lattice is equal to A. So A represents in this formula the lattice spacing, and gamma is the overlap integral due to the that accounts for the contribution of the, in this case, s orbitals of different ions, in particular two next neighbors, including also the contribution of the perturbation, that is the difference from the solid state potential and the atomic potential that is used for the evaluation of the core wave functions of the electrons. Yesterday, we saw what happens to the energy when we consider the situation where K is small, the modulus of K is small. And we saw that when K is close to zero, then the energy is equal to a constant plus an expression that resembles the free electron case. And we define the effective electron mass so that the expression that we find using the time binding model is equal to the expression that we found when we described the properties of the electrons in case we consider the free electron picture. Now, the second question of the exercise is the following. Describe, so point 2, describe the energy versus wave vector dependence I leave this question quite general due to the fact that the energy versus wave vector dependence in principle is a scalar field. So we should be able to plot the value of E for any arbitrary value of K, considering the fact that K is a vector. So in principle, we should again plot a scalar field. But what is done in general is not to do something like this because it's complicated to appreciate the three-dimensional structure of the E versus K dependence. But in general, one tries to, let's say, use a one-dimensional approach to represent the energy versus wave vector variation. And this one-dimensional approach is applied to specific directions. So if we suppose that this is the first Brillouin zone in the reciprocal space. So due to the fact that we use a simple cubic lattice, the first Brillouin zone in the reciprocal space is again just a cube. So the center of the first Brillouin zone is the origin of the space, and that point is usually labeled as gamma. So gamma, capital gamma, is the symbol that is used to identify the origin of the reciprocal space, or in this case, that is in this case, the center of the first Brillouin zone. Then what is generally done to represent the energy versus wave vector dependence is to start from gamma and follow directions of particular symmetry for the lattice. So in this case, one direction of symmetry is, for instance, the horizontal direction, starting from gamma and being parallel, for instance, to the x direction. And as you notice, due to the symmetry of the lattice, this direction is equivalent to the vertical direction. So when we move along the z direction, and is also equivalent to what happens in the y direction. So when we move along this direction. So again, due to the symmetry of the lattice, these three axes are equivalent with each other, and we just follow one of those. And in this case, we follow the axis along parallel to the horizontal direction, and the intersection point between that axis and the face of the cube is called x. Then another point of particular symmetry is the diagonal, another direction of particular symmetry is the diagonal of the cube. So one usually represents what happens to the energy as the wave vector as the value of the wave vector changes along the diagonal of the cube. So in this case, along the direction that goes from gamma, that is the center, up to this corner. So in that case, that corner is in generally called W. So the idea is to move, let's say, to represent the energy versus wave vector dependence, not in a three-dimensional fashion, but just in a one-dimensional one, following specific directions. So what I would like to do now is to, let's say, start from gamma, then from gamma go to x, from x move to W, and from W go back to gamma. So the idea is to switch from the representation of the scalar field to a representation of just a one-dimensional curve. And in this case, we represent the gamma to x, then the x to W, and the gamma to W. So we have a closed path that connects the center of the origin through the center itself, going through x and W. So again, this is not the full representation, but gives an idea to who looks at this diagram to about what happens again to the energy versus wave vector dependence. And this helps also for the, for instance, identification of energy values, helps in defining, for instance, if you remember the definition of the Fermi surface, the Fermi surface is a surface where the energy is constant. So in principle, is this group of all points where the energy has a specific value. So if you know what happens to the energy along specific directions, then you may have an idea of where along those specific directions the energy reaches a specific value, so that they may help to, let's say, build up a trial shape for what concerns the Fermi surface. But I will go on that later. So later we will try to find out what is the shape of a surface that corresponds to a specific energy using this energy versus wave vector dependence. So first step, let's try to see what happens going from gamma to x. From gamma to x, we move along the x-axis. If we move along the x-axis, we may use a sort of, let's say, parametric approach. So the arbitrary wave vector, in this case, is a wave vector that has the shape q00, where q is a positive number and 0, 0 are the y and z coordinates, due to the fact that now we are moving along the x direction. So using this value for the wave vector, we may just rewrite in this case e of q, where q is just a one-dimensional variable, that is equal to ES plus beta minus twice gamma of A. In place of cosine of Kxr, we have just cosine of Qr. And then in place of cosine of Kya and cosine of Kxa, we have just 2. So this is ES plus beta. Then we have minus 4 gamma A. And then we have minus twice gamma of A cos the cosine of Qa. So we may plot along this axis. We have Q in this case goes from 0, that is gamma, the center of the zone, up to the border of the zone. And the border of the zone is pi divided by A. In this case, when Q is equal to 0, the last term, so E of Q equal to 0 is equal to ES plus beta. Then we have minus 4 gamma, and there is an additional minus 2 gamma. So we have a minus 6 gamma. So this point here is ES plus beta minus 6 gamma of A. When Q is equal to pi divided by A, then we have ES plus beta. We have minus 4 gamma. And then the cosine, when Q is pi divided by A, we have the cosine of pi, so minus 1. So that changes the sign of the minus 2 gamma. So we have plus 2 gamma. So ES plus beta minus 2 gamma of A. So the value up here is ES plus beta minus 2 gamma of A. In between those 2 points, the dependence is the dependence of a cosine with the minus sign in front. So we start like this. And if you notice here, close to the center of the zone, the dependence resembles a parabola. That is what we found yesterday. That is that close to 0, the dependence is similar to the free electron picture. And if you notice, the same thing happens close to the border of the zone. But in this case, so you have again something that a dependence that resembles the dependence of a parabola. But in this case, the curvature of the parabola is opposite with respect to the case when we are close to gamma. So in this case, we have the free electron dependence, but with a minus sign in front. Let's say, as the gamma from W path is similar for what concerns the way to solve that to the gamma to X path, I will switch now to the gamma versus W path, and then at the end I will evaluate the X to W path. So now I go to the, so the first one is done. Then now I switch to the last one from the center to W. So from gamma to W, we are moving along the diagonal of the cube. And in this case, let's say when we moved along the X direction, we use the Q as a parameter. And in this case, in that case, the modulus of the vector was exactly equal to Q. So when Q increases from 0 to pi divided by A, the same is done by the modulus of Q. When we move along the diagonal, if we want to, let's say, find the parametric dependence that joins the origin to X, we have to make a choice concerning the structure of the vector. So in this case, the structure of the vector can be written in this way. If we, let's say, we have, as if we move along a diagonal, the three coordinates has to be equal with each other. So same coordinate in all the three positions. And we may use this as Q, Q, and Q. So same parameter. But to make, in order to have a vector whose modulus is exactly equal to Q, we have to take into consideration a normalization factor that is equal to the square root of 3. So the square root of 3 is there just to make sure that when you evaluate the modulus of that vector, that modulus is equal to Q. But this is just a choice. You may also do something different because that just scales the value of Q when you move along the trajectory. But in this way, when we set, let's say the initial point is 0, 0, 0. When we set the final point, the value of Q in that case will be pi divided by A. That is exactly equal to the border of the zone. If you do not include the normalization factor, then you have to take into consideration the fact that you have to scale Q to take into consideration the fact that, again, the modulus may be different from Q itself. So in this case, we may just rewrite the expression of the energy. So E of K is ES plus beta minus 2 gamma of A. And in this case, we have 3 times the same thing, that is the cosine of Q divided by the square root of 3 times A. So again, we have the exactly the same thing. And at this point, the dependence is again given by a cosine. So the initial point is always the initial point that we found before, because when we set Q equal to 0, we have minus 6 gamma A. So the starting point is always ES plus beta minus 6 gamma of A. Then what happens to the last point? And again, due to the fact that dependence is given by a cosine with a minus sign in front, we expect to have the same thing that we saw before. So a cosine dependence with a minus sign in front. So the question now is just to evaluate the final point of the of this dependence. Now, if we want to make sure that we access X, we have to set Q such that the modulus of Q is equal to the length of half the diagonal of the cube. In this case, we have that at the border, at the corner, is equal to the length, the side of the cube. In this case, if you just consider, I make here a plot. So we want to reach x up here. In this case, this is the diagonal of a cube whose side is pi divided by a. So the length of the diagonal is pi divided by a times the square root of 3. So in this case, we have pi divided by a times the square root of 3. And I use that as with the parametric expression that I use for k, the value of q is equal to the length of the vector that I use to access the points in space along the diagonal. So when I am at the end of the diagonal, I have to set in place of q exactly the modulus of the vector that joins the center with the diagonal. So using this approach, q represents the modulus of the vector. So when I do not have to set the 3 coordinates, but just the modulus of the vector that I want to use. So that's why I use pi divided by a times the square root of 3. And in this case, the cosine is q divided by the square root of 3, q is pi divided by a times the square root of 3 times a. So we have again pi, so a minus 1. So the last point in it represent the value es plus beta plus 6 gamma a. So what we see from that is that the energy variation along the x direction was just from minus 6 gamma to minus 2 gamma, so 4 gamma a of variation. Differently, when we move along the diagonal, the variation is of 12 gamma. So we have a huge variation of the energy along the diagonal, and there's a smaller variation of the energy along the x direction. So what is the consequence of that? The consequence of that is the following. When we will try, or in general, if we try to determine the shape of a surface of constant energy, that shape will be more extended along the x direction, y direction, and z direction, and less extended along the diagonal. Because along the diagonal, the energy increases faster with respect to the 3 axes. So a constant energy surface must have a sort of lobes along the axis and is more compressed along the diagonal. Because, again, the energy grows faster along the diagonal and slower along the 3 principal axes. So again, this is not a specific indication of the shape, but this is just the general indication concerning how do we expect that shape to be, how that shape should look like when you look for, again, the energy values that correspond to a specific value you're interested in, for instance, to the Fermi energy. Okay, so this was the second step from gamma to W. Just to join these 2 points, X and W, now let's try to move from the X to W. Again, the situation is quite similar since we have a cosine in the energy versus wave vector dependence. So we will always have cosine dependencies. What changes is just the range of variation. So that is the only difference. But anyway, I would like to make these 3 calculations, since now with this simple dependence, we will obtain, let's say, a picture where we have quite a simple variation when we consider the path that goes from gamma to X to W and back to gamma. But if we have this diagram in mind, when in a few weeks we will, let's say, we will not make a full calculation, I just show you the results. But in that case, when we will see the results of actual energy band calculations, the dependence will be slightly more complicated, but the idea will be always the same for what concerns the representation. So this calculation helps me to introduce you what is the general idea behind the method that is used for the representation of the energy versus wave vector dependence. So I make all the three calculations just to fix that dependence in mind, so we have that clear when in the next weeks we will see the actual results of bank structure calculations. In the last case, we have to move from from x, whose coordinate is pi divided by a 0, 0. So this is x. And we have to move to w, and w is pi divided by a, pi divided by a, pi divided by a. So this is w. So in this situation, we may use a parametric representation of k that is equal to pi divided by a, since the x coordinate never changes, and then we have t times pi divided by a and t times pi divided by a. So just a coefficient in front of pi divided by a that allows us to join the center of the one of the sides of the cube to the corner when we have access the diagonal. So in this picture, the energy versus wave vector dependence is E of s plus beta, then we have minus 2 gamma of a. The first pi divided by a gives us a minus 1. And then we have plus the cosine of t pi divided by a. And I add the two factor, since the x and the z, the y and the z component has exactly the same dependence. So in this picture, what we have is Es plus beta. Then I have plus 2 gamma of a, and then minus 4 gamma of a times the cosine of t pi divided by a. So when t is equal to 0, so we start from x. In this picture, the value of the parameter that we have on the horizontal axis is t, and t goes from 0 to 1. 0 represents x, 1 represents w. So in x, if we set t equal to 0, we have 2 gamma a minus 4 gamma a. So we have the EES plus beta minus 2 gamma a, that was the value that we found for x. And the final value is t equal to 1, in this case. Sorry, not 1, otherwise the, I forgot the a, sorry. If I set t just as a parametric value, in the cosine I have pi divided by a, that is not fine, since I have something that is expressed in the meters to the minus 1. So the correct thing is not to set t, but t times a. So in this way, I have a simplification of a and a. And so here, no. I'm sorry, I make a confusion since I forgot the a in the dependence. That's why the thing were not fine. So I missed the a that I have in the kx, ky times a cosine dependence. So if I simplify a and a, then when t equal to 1, here I have just pi. Cosine gives us a minus 1, so I have Es plus beta plus 6 gamma of a. That is what we found for w. So again, we have a cosine dependence. And please note that here, the dependence is again similar to a parabola. So this means that if you look at the energy values close to x, so if you suppose to look at what happens on one of the sides of the square, close to the center of the side, as you see from that diagram, when you move from the center of the side to the corner of the side, the initial part of the energy versus wave vector dependence is parabolic. So this means that the constant energy surfaces, or in this case, since we are actually on a plane, we are on one of the sides of the cube. So in this case, we have no surfaces. We have just lines in a two-dimensional space. So in this case, the lines that correspond to constant values of the energy are circles. So starting from x, if you want to draw the lines that represent the areas where we have a constant energy, then we have circles. And this is again similar to what we found at the center of the zone. In that case, we had spheres because we were in a three-dimensional space. In this case, we have made a cut, we just work on a surface. So in this case, we have circles. And at this point, we may join the three dependencies and plot in just one graph what happens when we move from gamma to x, w, and then back to gamma. So to make the full representation, we may use this graph. So vertical axis, energy, horizontal axis, position. We start from gamma, then the first step is to reach the side of the cube, so x. Then we move from x to w, from the center to the corner, and then from the corner back down to gamma, to the center. The energy corresponding to the, let's say, to gamma, so the horizontal value of the energy is Es plus beta minus 6 gamma of A. So that is the minimum energy value. Then we know that when we reach x, the x value of the energy is Es plus beta minus gamma of A times 2. The value that we have in W is Es plus beta plus 6 times gamma of A, and then we go back to gamma, to the initial point. The gamma versus x, along the gamma x direction, we have the cosine. The cosine dependence. Then when we switch from gamma to W, again a cosine dependence. And then when we go back to 0, we have the same dependence, but in this case, we have to make the symmetrical one, since we are not going from gamma to W, but we are going from W to gamma. Okay, so in this way, we have been able to represent, using just a one-dimensional picture, the energy versus wave vector dependence following specific directions. Again, this picture has less, the amount of information that you have in this picture is smaller with respect to the amount of information that you have in the full dependence. So for sure, the full dependence is an amount of information that is larger than the amount of information that you are able to access using just this diagram. But this is a simple way, easy way to access the details of the dependence, just again using a one-dimensional representation. So this is the representation that we usually find when looking at the results of bench structure calculations. And in general, the path that one follows are paths of, again, particular symmetry for the lattice. In the case of the cubic one, we have the axes that are orthogonal to the three sides of the cube, and the axis that goes through the corners, so the diagonal of the cube. So that's why in this picture, I followed those directions. In case you have a more complicated cell, for instance, an FCC lattice or a BCC lattice, again, you may follow, for instance, the directions that go perpendicular to the sides of the cell, or the directions that go, for instance, from the center of the zone that is always called gamma to one of the corners of the Brillouin zone that correspond to the lattice you are investigating. So this is the usual approach. And the last step is to, let's say, try to do what one generally does when one tries to determine the shape of the Fermi surface. So we have to, at this point, to find the shape of a specific surface, we have to fix an energy value and try to find what is the shape of the surface that includes all the points where the energy has exactly that value. In this case, just to make an example, since the result is quite interesting for me, we may use as a constant value, so the reference value for the energy, we may use the energy that corresponds to the x position. That means the energy that is found at the center of the side of the cube. So the constant energy value is Es plus beta minus 2 gamma A. So that is the value that corresponds to the x position, the center of the side of the cube. To access that, we may just compare the general dependence to that specific value. So in this situation, ES and beta may be simplified. We are left with minus 2 gamma on the left and minus 2 gamma on the right. So we may also divide everything by minus 2 gamma A. So at the end, after the division, we have the cosine of kxa plus the cosine of kya plus the cosine of kza that is equal to 1. At this point, let's say to solve this equation may be complicated. So one possibility to find a solution is to let's say, decided to investigate the solution only along specific directions. For instance, one may try to see what happens if we make a cut of this surface using as a reference plane the xy plane. So what we may try to do is to set kz equal to 0. So just to see what happens along the horizontal plane. So if kz is equal to 0, then the last cosine is equal to 1. So we have 1 on the right side and 1 on the left side. So we may simplify the two ones, and we have that the cosine of kxa plus the cosine of kya is equal to 0. That can be solved remembering the, I don't remember the exact name of those equations, but if you have a sum of cosine, the sum of cosines, you may rewrite that sum of cosines using this expression. So twice the cosine of kxa plus kya divided by 2 times the cosine of kxa minus kya divided by 2, and that should be equal to 0. So the first part of this equation is just the equal to the initial one, just using the summation formula for cosines. And in this case, the solution is easier since we have, apart from the two factor, that the product of two cosines has to be equal to 0. If that is equal to 0, then we have that what is within the cosine has to be equal to pi divided by 2 or minus pi divided by 2. So at this point, we are left with, let's say, 4 different equations. And the 4 different equations are the following. So kxa plus kya divided by 2 has to be equal to plus or minus pi divided by 2, and kxa minus kya divided by 2 has to be equal to plus or minus pi divided by 2. In principle, you may say not just pi divided by 2 is fine, because for periodicity, I should use also higher values or smaller values for what concerns the reference angle in radians. But if I do that, I access kx and ky values that are out of the first zone. So that's why I do not use I do not add any additional pi for the solution of this equation. So I have in mind the fact that kx and ky, okay, has to solve the equation, but has to be within the first Brillouin zone. So that's why we do not use higher values for the reference angle. In this picture, we may try to express these two, rewrite these two equations as ky as dependent variable, writing ky as a dependent variable as a function of kx as independent variable. So if we use equation 1, equation 1 can be rewritten as, after the simplification of the two factors that we have here, so we have kya is equal to plus or minus pi divided by a, just pi, minus kxa, or ky equal to plus or minus pi divided by a minus kx. If we represent that is a straight line, the equation of a straight line, and that straight line has a negative slope. That line intersects the ky axis in pi divided by a. The slope is equal to 1, so it also intersects the horizontal axis in pi divided by a, and it is like that. And if in place of plus pi divided by a here, you write minus pi divided by a, you have another straight line that is parallel to that, but that intersects the vertical axis in minus pi divided by a. So if for you is fine, now I just change the page so to make a single plot with both lines. So in this case, we have kx, ky, so we have one line like this and one line like this. And these two are the solution of the equation that I labeled as 1 before. And so 1 was the kxa plus kya divided by 2 is equal to plus or minus pi divided by 2. If we consider now equation 2, that was kxa minus kya divided by 2 is equal to plus or minus pi divided by 2. In this case, due to the minus sign in front of ky, we have again straight lines, but in this case, the slope is 1. So the lines corresponding to the equation that I labeled as 2 are this one here and this one here. So we have two parallel lines corresponding to solution 1, to equation 1, two parallel lines corresponding to equation 2, and they form a square. So within the first zone, in particular within the xy plane, let's say the intersection between the constant energy surface and the xy plane is a square. If you now apply the same method to the zy plane or to the zx plane, you always find squares. So the intersection between that surface and the plane gives you always a square. At this point, if we try to represent the three-dimensional, if we try to obtain a three-dimensional representation of this solution, then I will try to do my best. Please use your also your imagination here. So kx, ky, and kz, the three axes, what we have is here we have a square, then we also have a square up here, and then we have another square in the orthogonal direction. So we have like two pyramids, one above, so one above the XY plane, and the first pyramid is this one here. So the base of the pyramid is a square, and we have one of those in the above the XY plane, and the second one is below the XY plane. So we have these two pyramids, one above the other. In one case, one points upwards, the second one points downwards. And if we try to make just a two-dimensional representation of that, if you look within the first Brillouin zone, so if we have Kx, Ky, the zone is so the first the first Brillouin zone is a cube. In two dimensions, we have a square. So this constant energy surface is a square that is rotated by 45 degrees with respect to the square of the first Brillouin zone. So diciamo un quadrato, sì, tipo un quadrato che ha i vertici nei punti di contatto fra gli assi e la prima zona. Yeah. If I may use just additional 5 minutes, at this point, let's say the choice of the constant energy value that I used as a reference was random in this case. Let's say we didn't try to make a calculation, for instance, considering, I don't know, the number of electrons in the sphere, sorry, the number of the electrons in the system, and according to that, we may evaluate the Fermi energy, and so we try to find exactly the shape of the Fermi surface. So this was just an arbitrary value. I knew that the solution was simple, and so we were able to solve that analytically quite fast. At this point, one question could be the following: how many electrons are included in that surface? So if we now want to determine how many electrons are found within this constant energy surface, how is it possible to evaluate the answer? So once we have found the shape of that surface, the question is how many or the same question is how many levels can be found within the surface, because we never spoke about actual electrons here. So a similar question could be how many levels, because we know that one level may host up to 2 electrons. So what can we do to answer to that to this question?
Number of levels inside the ball is constant, you know this value, and then
Okay, so the suggestion is to evaluate the volume of this constant energy surface, and we may compare the volume of that surface also with the volume that we know how many electrons includes or how many levels includes, because the volume, if we compare that volume with the volume of the first Brillouin zone, we know that the volume of the first Brillouin zone includes n levels or 2n electrons. So if we make the ratio between the volume of that surface and the volume of the first Brillouin zone, that volume is the ratio between, let's say, that tells us what is the fraction of levels that is included in that volume. And if we know the fraction, we know also the number, because we know the number of levels that can be included in the first Brillouin zone. So after making the calculation, then we have the fraction of levels that are included in that surface. And concerning the volume of the first Brillouin zone, the volume of the first Brillouin zone is just the volume of a cube whose side is 2 pi divided by a. So in this case, the volume is 2 pi divided by a to the power of 3. In the case of the constant energy surface, we may use the fact that we have two pyramids. So this 2 factor is due to the fact that we have two pyramids. Then the volume of a pyramid is obtained by multiplying the surface area times the height of the pyramid and then divided by 3. So I have 1/3. So this is just the division by 3. Then the height of the pyramid is half of the first of half of the side of the zone. So is pi divided by a. Then I need the area of the surface. The area of the surface is the area of a square. Now we have to evaluate the side of the square. If you notice from this diagram here, this length is the side of the first Brillouin zone, but is also the diagonal of the square. Due to the fact that there is a connection between the side of a square and the diagonal of the square, we may evaluate the side of the square just by taking the length of the diagonal and divide it by the square root of 2. So the side of the square is length of the diagonal, that is 2 pi divided by a, divided by the square root of 2. And this is squared. So we have below, we have 8 pi to the power of 3 divided by a to the power of 3. Then above we have 2 divided by 3. Then we have pi divided by a. Then we have an a squared and also a pi squared that come out from the parentheses. Then within the parentheses, we have 2 divided by the square root of 2. So we have a square root of 2 at the numerator. Once we apply the square, we have just 2. So we may remove the pi and also remove a. So we are left with 4 divided by 3 at the numerator and 8 at the denominator. So this is equal to 1 divided by 6. See, yes. So 4 divided by 8 is 1 divided by 2 times 1 divided by 3, so 1 divided by 6. So this means that within that constant energy surface, there is 1/6 of all the possible levels that can be included in the first Brillouin zone. So if we want to make a calculation concerning the number of electrons, then the number of electrons is 2n divided by 6. So we have a total number of n divided by 3 electrons that can be hosted within this constant energy surface. Okay, and this was the last step of the exercise. Do you have questions or comments concerning the calculation? Okay, if you do not have questions or comments, we can make a break. So now I stop the registration.